I think I'm known to many of you here, but my name is Julio Tino. I'm the Dean of McCormick. A culture thrives by the interaction of all its parts. I love that phrase because it scales, okay? In fact, it applies, if you want, to Segal. And once in a while, you take a look and see that there are parts that could be there that are missing, and then you go in a campaign looking for what parts will bring value to Segal. And you probably notice that there will be a series of talks, of which this one is the first. And this is kind of new ideas that are supposed to diffuse through the Segal design community, okay? So there will be maybe about 7 of them. Normally the talks will be given in pairs. So this is the first one. So the idea is to bring components of design that were not part of the core of Segal, and this happens all the time, that now should be part. So the idea is to communicate ideas, and what I would encourage everybody when they hear ideas, because this is a curse of over-analytical people. When they hear ideas, they want to put the idea in the little library that they have in their heads, and if it doesn't fit exactly, the idea gets discarded. The idea is to have ideas for future use, because anything, even if you disagree completely with the idea, having somewhere in there is a good thing. So, but the idea is expand your thinking space, okay? So I think starting with Mike Peshkin and David Gatchell is a fantastic way to start, and I want to see all this enrichment that will happen by bringing new blood into Segal. Gentlemen, the floor is yours. Thank you.
Thank you, Julio. Am I coming through okay? All right, good. Yeah, I'm Michael Peshkin. I'm here with David Gatchell today, tell you some stories, hopefully at the connection of education with design and practice. And we're going to each tell you a little bit about our own stories first, and then march into 3 or 4 stories from our experience here, elsewhere, startups, etc. So, and I'll ask for your input at a certain place, and so will David. So first, a little bit about me. I've been here in the, I don't need this. I've been here in the mechanical engineering department for much longer than I want to think about. And my area of research and also of entrepreneurship, I'll be bringing stories today from those activities, has been in the physical interaction between people and robots. How should people and robots work together when they are working together physically, as opposed to emotional interaction, visual interaction, information interaction? I'm part of the team that designed our Engineering First curriculum many years ago, and I'm also founder of 4 spin-offs. 2 of the stories today will be from those. And I've also had good experiences with our Invention Patent Tech Transfer Office, Innovo. And in fact, my proudest invention is this one, the Lightboard, which is for making video lecture recordings. And that thing is now in Mud Library, and anybody who wants to make a video recording with that can go and do that. So we teach a lot of sort of good design practices and principles, and one of them that I especially like is fail early, and the idea being before you get too far into a project with your great ideas and what you think you're doing, build quick prototypes, try stuff out, get user feedback, find out as early as possible if you are on the wrong path, which you probably are, and that's so much cheaper and faster. And the stories I'll be telling today are of that nature. It's much more fun to talk about things that don't work the things that do work, at least to begin with. But I don't want you to think that everything I do doesn't work. So I'm going to run through just the names and sort of you'll see the theme of these 4 companies that I've been involved with. One of them, which I hope I'll get to a story from, is in the area of image-guided surgery. And this was originally called ZCAT, later Mako Surgical. And the idea was how should surgeons and robots interact? Hopefully, you'll see this theme over and over again. Hopefully not by displacing the surgeon and making a robot surgeon, but rather by bringing the best of both to the activity. And that company was bought in an amazingly large purchase in 2013 by Stryker. And had I stayed involved with that company through thick and thin for like 10 years, I would be on my yacht right now. In fact, there were 5 co-founders of that company. One of them did make a lot of money, isn't on his yacht right now. And I was talking to him in preparation for this talk, and he's now able to be his own angel investor. When he has an idea, he can just go do it. So plenty of money, but only if you really stuck with it. The other 3 of these I did jointly mostly with Ed Colgate, an occasional other. So he's the co-founder of the next 3 companies I'm going to tell you about. Cobotics. And here the idea was similar to integrated surgery, but now it's in manufacturing and in assembly, especially in automobile assembly, but other materials handling applications. What's the proper interaction between people and robots there? And we found that the people that you'd most expect to be fearful of robots, because the robot is supposed to take our job, were not fearful of these cobots, collaborative robots, because they understood that the idea was to complement their abilities with robot abilities rather than to try to make autonomous robots that replace them. So third, and I'll have a story from this one as well, Kinia Design in the space of rehabilitation robotics. So again, there's a clinician working with that'll be my first story, working with a patient, and how do you combine, is there a role to combine robotics with the skills that a physical therapist brings to a patient rather than trying to do what the physical therapist does? And lastly, and this one is current, the only one that has not been gobbled up, is Tanvis. And this is not about people and robots, but it still is the physical interaction of people and machines. In this case, how can you spend all day swiping touchscreens. Why can't you get anything back from that touchscreen besides an occasional buzz? Why can't you feel real textures and structures on that touchscreen? So now I'm going to hand this over to David to introduce himself.
Can everybody hear me okay? Okay, excellent. One thing that we decided is that when we were speaking, we'd take our masks off, and when we were watching, we'd put our masks on, send that message. Michael, I want to take 30 seconds just to talk about a little bit, just building upon what Julio said. We had never interacted in this level of detail, this amount of time before. And it's a real privilege as someone who is junior and has looked up to Professor Peshkin over the 10, 11 years that I've been here to have an opportunity to collaborate to put this talk together. I really feel like I learned an awful lot. And at the very least, the ability for us to collaborate in putting this talk together was well worth it. And so I thank you for the opportunity to do so.
It was great.
So most of you in the audience know that I'm the director of the Manufacturing and Design Engineering program here within the Segal Design Institute, but I did have a life prior to that. And this next slide is a set of images that captures that. In no particular order, I grew up in Maine, so I'm a transplant. I moved to Chicago in 2003. It's a picture of the Portland headlight in the lower right-hand corner. And above that is Bowdoin's Art Museum. I went to Bowdoin College as an undergraduate and studied physics, and that's why I have that picture of Albert Einstein and some mathematical images there. After graduating from Bowdoin, I moved to Boston. There's a picture of the Charles River and Commonwealth Avenue, which goes right through the heart of Boston University, where I studied biomedical engineering. Once I finished my PhD, I came to Northwestern in 2003 for a postdoc in biomedical engineering, which focused on engineering education and how people learn. And what you have there is you have the landmark publication from 1999 by the National Research Council, which really talks about how to teach and how to get people to understand complex principles like you have in engineering. And there are learnings from how people learn that inform my pedagogy today. During my time at Northwestern, I've worked on a lot of different projects, but I've captured a couple images of some of the more interesting ones. In the upper right-hand corner, you may remember this image from one of the Northwestern alumni magazines as a picture of Dr. Rob Murphy traveling to Timbuktu to talk to a local physician to understand some of the needs that the people have there. I was fortunate enough to travel to Nigeria for a number of years with Dr. Murphy to help the University of Lagos and the University of Ibadan develop biomedical engineering programs. In the center top, you see a picture of Mr. Jim Elliott, the founder of Dive Heart, actually scuba diving with a woman who lives with quadriplegia. Mr. Elliott is the founder of Dive Heart and uses scuba diving for therapeutic purposes, and we've done some projects with him over the years that have been quite challenging. Well, as I mentioned, just reminded many of you, I am director of the Manufacturing and Design Engineering program, the MADE program. And just a little bit about it in case it's new to you. It was founded in 2002. Bruce Enkelman can take credit for pulling that together. First graduating class was 2004, and it was a whopping 2 students, one ME MADE and one IE MADE. I joined as director in 2011, and you can see in this bar chart to the right, there's been some significant growth in the program during that time. The orange bars that you see in that bar graph show students who started off as MADE majors but ended up pursuing an integrated engineering studies degree because it wasn't a product-focused major that they wanted to pursue, but maybe something in experience design. On the left, you can see what the MADE program really brings together. It brings together coursework from 4 different departments within the McCormick School. Human-centered design, the courses that our students are required to take within Segal. Courses in optimization and project scheduling, which they take in the industrial engineering department. Courses in manufacturing and geometric dimensioning and tolerancing, which they take in the mechanical engineering department. And then, of course, the ubiquity, if you will, of materials and material choice and material design, which allows our students or has our students taking classes in materials science. For the last 3 years, we've actually introduced a new MADE capstone class, and many of those students in this year's cohort are in the audience today, and I'm going to ask you to participate as we begin our stories here in a few slides. It's a new 3-quarter capstone, and I'm going to just show a few of the results from the past couple of years. So this first one is a Fitbit for Trees, which was done in the first year of the capstone in collaboration with Morton Arboretum. This next one was also done in that first year of the capstone with a forestry division of the city of Evanston, and it's a soil moisture sensor. This next one, actually, I have a prototype, is a collapsible suitcase. And what's really interesting about this project is that in working with my colleague and co-instructor, Professor Dan Brown, this team was not only able to create a collapsible suitcase, they were actually able to design the manufacturing process to make it cost-effective to manufacture in the United States, cheaper than actually making it in China, which was probably the major breakthrough of this project. The next one is actually a wall-mounted module for sanitizing stethoscopes. The team identified that there's a compliance issue among medical professionals in that space. And the last one I want to show is maybe something that's you experience personally. You haven't thought ahead. You want to put some chicken or a steak or something along those lines into your meal. This team actually came up with something called the Penguin, which allows you to thaw up to 2 pounds of meat within 20 minutes, both safely and without compromising up the flavor of the meat. Okay, so we're going to get started. As I said, it's design stories, and our intent is to share up to 4 stories. So let's get started on the first one. All of us have probably experienced breaking a glass or 2 over our lives. I want you to think about the last time you did this. What problems did you experience as you tried to clean it up? To give you 10, 15 seconds to think about that. And I'd like to hear from the audience. What? Very small pieces. Cutting the trash bag. Your hands got bloody. Excellent. Excellent. So we had a team in the first capstone year that focused on this project. And they explored the needs not only of people like you, but the needs of multiple stakeholders. And using the consumption chain, they were able to explore the needs of not only people who are cleaning up broken glass in the home, but people that actually manufacture glass, people that might ship glass, and they identified a whole bunch of needs. Through that, what they determined is that there are 4 functional needs that everybody has. And those come down to identifying the glass, removing the glass, verifying that you've picked up all the shards, and then disposing of those pieces. And we heard a little bit about those needs as you guys volunteered your thoughts. They also identified that there are a whole bunch of workarounds and current solutions, including some unexpected ones, like using a potato cut in half, or a slice of bread, or even a can of Play-Doh. So what do you think they did? They had to do some benchmarking. They had to understand how these workarounds work, what their strengths are, and what are their weaknesses. And so they'd identified a bunch of different environments in which glass is used and in which it's broken, the different types of glass in which can be broken. And what they decided to do is what we often tell students to do: bring focus to your problem. And that's what's been highlighted in pink. They created a test bed in the sub-basement of Ford in the old EDI studio, and they were able to interchange the floors. And through their benchmarking, they tested 9 different cleanup methods on these different floor surfaces against these needs. And they created this impressive benchmarking matrix. And from that, they were able to determine that different methods do very well with different sized pieces of glass. They also determined that the ability to see the glass is a key differentiator. That's often one of the reasons, Tino, you said that. You've got to be able to find the glass. So their final problem statement was to create a comprehensive solution that addressed these functional needs. They brainstormed a whole bunch of different ideas. They did some early stage mock-ups. They tested promising features on those mock-ups. And then they did a series of iterations through off-the-shelf solutions and then CAD designs that they were able to 3D print. By the end of the second quarter, they had this works-like prototype, which encompasses a dustpan with a vacuum with a glass catcher on the back end of that vacuum head. Well, one of the things that I said was a differentiator was the use of light. So an LED exploration was necessary. So they looked at different wavelengths of light. They used different types of LEDs. They used different types of filters. You can see here some of their exploration. They ended up doing some product dissections to see if they could actually use off-the-shelf solutions to make their prototyping process easier. And they determined that a COB LED was actually used in some of these high-intensity lights. And they were able to get the form factor right so they could fit it into their prototype. The last quarter, this team, and this is kind of foreshadowing for the MAID students, they really focused on design for assembly and design for manufacturing. And that's where a lot of the technical work ended up playing out in this class. So they looked at different features that would allow this product to come together, like alignment bosses and press fits. They determined that a living hinge would allow the top and bottom to come together. And there's more about that when we start talking about manufacturing considerations. And they looked at different types of fasteners to allow these pieces to come together. On the manufacturing considerations, a lot of those pieces you just saw could be injection molded. And they worked with a local injection molding company to co-design their solution so it could be injection molded in a cost-effective way. And one of the students, Lucas Pagni, actually took it upon himself to use SolidWorks plastics to do some of the simulations that you see here so that he could understand how long it would take for that plastic to cool, what the flow patterns would be, what the impacts are of different dimensioning. And by the time he got done, he was able to come up with some very informed cost per part projections. And another thing that materialized, which I think is probably going to be new to you, and it was new to me in a sense because I haven't brought a lot of products to market, is a new set of manufacturing requirements. We often think that we set our needs and our requirements and our specs early on in the design process. Well, when you get to this level of manufacturing, you have to set these targets. And that's what you see here. And they were actually on target for all of their requirements. So they did a similar analysis for their assembly costs. Okay, and so here you see just instructions for putting together all of these different components. And they did time value studies so that they could actually estimate the cost per part of assembling this in a factory. And it came out to about 96 cents. Well, their final solution is pictured here. On the left is a rendering, an isometric rendering, or a rendering of an isometric view, and on the right is a front view. Here's an exploded view. You can see all the different components that went into what is a fairly simple product. We have a couple of images here, and then here's an image of the working prototype in its dustpan mode, and here's a picture of it in the vacuum mode. And the last thing I will say with this, it actually was entered into the Dyson design competition. And if you look at the most recent Dyson vacuums, the cordless ones, they integrate a blue LED into their vacuum. So I find that kind of interesting. Right. Thank you.
Thanks, David. What I love about that story is how the students started out in our needs finding and the design process that we teach here. And before very long, they're lost in mold flow and cooling rates and design for assembly, and they sort of moved into from the conceptual design into the technical design, into the engineering design. So that's beautiful to me. So okay, so whoops, you forgot to mention your team there. All right, we'll have to come back to them. So this is the Kinia Design company that I told you about to begin with. And we had the unusual opportunity to do, this was with Ed Colgate and a professor in physical therapy as well. We had the unusual opportunity to kind of do a blue sky design. Like the charge was, see if there is any role, what is the role, for robots helping physical therapists. And all we really knew was we weren't going to try to build a robot physical therapist, not the concept. So, of course, the first thing we did is a whole bunch of observations. And this is a typical physical therapy gym, and you don't see a lot of robots there. In fact, you don't see a motor there, or really hardly anything that qualifies as a machine except in the most basic sense of a machine, like something with a lever or a wheel. I'm going to talk about the team, but that was all you're going to see of them for now. But I'm coming back to them. Team is, of course, important. That's part of my talk, what I'm trying to say. We'll come back to them. Here's what we saw in some of our observations, though, that kind of suggested to us there might be some opportunities for powerful machines. So a couple of things we saw were stretching exercises, range of motion exercises, and these typically involve large forces, typically small clinicians, and large patients. And you can think about, I'm going to ask you about what some of the issues or needs might be there. Also, gait training. This is kind of an extreme example of gait training, trying to learn to navigate stairs. But you can see what the clinician is doing and struggling with, and that's a small patient. That's a very small patient. Most patients are much bigger than that. So those inspired us a little bit. Let's see if we could come up with some concepts for how we might do something with robotics technologies to assist in those things. And so here's what do you know? Brainstorming, coming up with ideas for how to how to unweight people's legs so that they can better work on the motion of their legs, not put quite so much of their body weight on their legs. So body weight support, and we'll look at this a little bit more later, but you can see there are lots of wild ideas in here, many of which we actually kind of explored at some depth. And having chosen a few possible directions, I'm going to illustrate some ones that did not turn out to be where we went. So in a minute, I'll tell you what these are, and then I'm going to ask you, unfairly in a certain way, to tell me what might be wrong with those directions. Okay, so here, bicycle exercise devices are popular in rehabilitation, and this is a simplest possible works-like prototype to check out that idea with users, with us, with experts. Bicycle upside down, and what's this thing? The addition here is that you should have some upper body motion, that your body should be able to, that controlling the motion of your upper body should be a feature of doing this exercise in a way it doesn't usually get to be. And this thing is a board full of rollers so that you can squiggle around. Your back can squiggle around on this thing as you attempt to bicycle. Okay, that was one concept. Here's a same blue upper body motion support thing here, so you can wiggle around your upper body, but now it's based on treadmill, also a popular kind of rehabilitation exercise. And here was a third concept we went into called the physiatrist's workbench. This is for those stretches and range of motion exercises that I showed you required such large forces. The idea would be sort of a versatile bed-like structure with movable parts, but also with some robotically, it's not a robot at this point, but some powered arms that could, in a very controlled, slow, measured way, apply those stretching forces to limbs. Okay, so that was 3 concepts, all of which we rejected. And I'm going to ask you this unfair question because, you've all broken and tried to pick up glass. That's a fair question. But you haven't probably been in physical therapy or know much about physical therapy. Nevertheless, I'm going to ask you, what criticisms might you have of the directions, not necessarily the specific devices, but the directions we've chosen to go here? Anybody? Yes? Okay. So even getting into a cycling device could be a challenge. You should have been on our team. We could have saved some time. Others? Yes?
I think in general, these solutions lack reliable feedback. But I also think the one on the left specifically is I would be worried about when someone is trying to use it, they might push with their legs instead of being able to reliably pedal, especially if they're not used to using their legs, then they might end up pushing themselves backwards.
Okay. Yes?
This is in a lot of ways just a function of the way a prototyping process works, but a lot of these look very industrial and very scary and that's these pictures you showed, which had all these childlike toys and they were very soft looking and comfortable, which might have had the users being apprehensive.
That one I'm going to say no fair. These are just works like prototypes. Yeah, they look industrial. But I think about this one, maybe that's going to stay true, right? Anything that involves movable constraints to push against robot parts is going to stay looking kind of spidery and scary. Yeah. Yes? So that would especially be a criticism of this one, right? Yes?
I worked on a similar project, tangential to this at one time, and I remember, and I'm wondering if you've considered this as well, is the fact that for physical therapy, there needs to be signs of progress. And so these solutions seem to be lacking a way to measure how much weight a person is able to start supporting after they work on it.
Okay, but I would claim, at least on this one, that previously the physical therapist doing these stretches manually is like estimating, and 3 significant figures digital readout of how many degrees or how many pounds might be a benefit of doing it with the machine. Yes?
I feel like physical therapy, I don't know, looking at these 3 devices, it feels like they're created a very
Okay, yeah, I like that. You should have been in our team too. Any others, or shall I? Yeah.
I would say that middle one, people are not really one size fits all. I think it's part of the physical therapy is because it's a person sort of moving another person, it's so tailored that I think it would be hard to be a machine to create something that you could tailor so well to someone's different.
Yeah, clinicians here are amazingly versatile. And as you saw in that picture, using their bodies in as fixtures in very versatile ways. Yeah. Good, thank you. That was really useful and, would have helped. So this is not the direction we went, and I will tell you a couple of reasons. Well, why don't I do that right now? The one that I found actually most fascinating for that, one of the reasons we rejected this one and this one, just one of the reasons, those were good reasons too, were that really that degree of upper body motion was not adequate upper body motion. I mean, we're trying to recapture some of the, doing an exercise with your upper body free is not the same as doing the exercise when you're just trying to do a couple of muscles. And these really did not manage to capture that well enough. This one I found especially fascinating, kind of for the reasons you said, because it turned out that that activity of stretching is, as one of you said, is a moment of connection between the physical therapist and the client, and they can feel what's going on with that client, and they establish something. I don't think you used the word trust today.
I haven't.
But they establish trust with that client. This is going to hurt, but I'm not going to hurt you. Like that. And I guess I realized the strong connection between pain and dread, right? Like if you have a machine that, even if it's a very good machine and I promise it's going to stop as soon as I push this button or you say stop, and it's never going to suddenly do anything, you don't trust it the way you may trust your therapist. And that in the context of being afraid, everything hurts so much worse, and this exercise has to hurt. So we can't afford for it to hurt much. So I found that, so trust came, in our conversations, trust came up several times, and we went like, trust. I wonder if that's part of human-centered design in some way. We should think about that. Okay, so we rejected these and went on to something a little more flexible. And here are some, you'll recognize these from our process too. Little mock-ups of some ideas for how could somebody walk with some body weight support, unweight their legs, but with greater upper body motion available. And part of the building, prototyping, trying. So here's a quick prototype for how can we support somebody's upper body so that they can still move freely, but we won't let them fall over, they won't let them go too far. As this became more and more sophisticated, it became really a robotic device. It was designed to go over ground, so you could actually wander around the halls, walking with this thing holding you up somewhat at the hips, letting your body move so you can work on balance. The idea was that the physical therapist could, this is not a patient, this is an engineer, could actually do things with you that they would never be able to do safely if they were responsible for holding you up. And it would pretty much just hold you there, maybe unweighting you, and if you fell over, it would catch you. So they could give you a shove, they could make you reach for a ball, do all sorts of challenging things, and the job of the machine was to hold you up and catch you if you fell. So that became a device. Now, I promised I'd go back to the team, okay? And I want to talk about teams a little bit, like who do you want on your team? Well, first, I have to warn you, if you ask me who should be on your team, you're going to find out what you need is a whole bunch of college professors on your team. That is an artifact of, it being me, right? So I'm going to ignore the college professors here, of which there are too many. And so there are people on a design team. This is not all of them, but it's sort of most of them. Some of them are domain experts, like Ela Lewis, who is a practicing clinician, a practicing physical therapist. Some of them are process and industrial design and psychology experts, like Amy Schwartz, who was at IDEO at the time and is now here. Some of them are a couple of engineers I wanted to say something about. Like what kind of, so 4 engineers. Like there's a lot, we got some, for instance, there could be industrial designers. We got some industrial design services actually through IDEO, so those people are not represented here, but they would be reasonably part of a team. But what about those engineers? Here are 2 engineers. That's Alex Mocklin and that's Julio Santos Mune. And he has a double E degree from University of Illinois, master's degree, and he has a master's degree in mechanical engineering from right here. And They are extraordinary engineers. And I think what I want to contrast here is, mechanical design, learned plenty of programming, okay on control, on automatic control, okay on electronics. Fantastic electronics, fantastic controls, very good programming, not a lot. Anyway, they bring like wizard level skills at something. And to me, I wanted to talk about like, how do you wind up, what makes you be a valuable participant, a valuable member of a design team like this? If you're an engineer, there's other routes on too. But if you're an engineer, I think it's that you really want technical wizards on your team. And these are the most productive and valuable kind of versatility is great, but you really want somebody who has a wizardry level understanding. And I just wanted to go back to this picture a moment while I say that. Like, can those people who are really immersed in their discipline and really expert at what they do, can they think out of the box and brainstorm wildly and interact with people well, look, one of our pictures here of how to hold people up had helicopter blades. Okay, I don't think that was that useful, but there was no problem thinking out of the box, right? People are way out of the box. No problem with that. And so my takeaway from this is wizard level engineering skills, learn design process and teamwork, and that's what makes you the most valuable engineer on a team. Okay, I think I'm handing this over to you.
I think you are too. All right, thank you. So I want to complement what Professor Peshkin just said. I think in addition to the technical wizardry is the resourcefulness, particularly among undergraduates in design classes. And so the next story we're going to talk about is an example of students reaching out when they didn't know something and being guided by someone with that technical wizardry, which they could then take home after that experience. So we're going to talk about a fish story. So, who likes to fish? Just show of hands. I like to fish. Not too many fish? Okay. Anyone use lures when they fish? Okay, pretty much everybody who wrote. What kind of hooks do lures use? Go ahead, Claire. Say again, barbed? Okay. Single hooks? Treble hooks? Liam? Say again? Sharp? Yep, very sharp. Go ahead. I can't hear you. Okay. Okay. Well, I often fish with something called a jitterbug. Anybody know what these hooks are called? They're called treble hooks. And if you have experience with treble hooks, there are quite a few problems with them. Anybody guess what might be problematic about a treble hook?
If you're actually lucky enough to catch a fish, it's really hard to get out because oftentimes you'll have the whole fishing rod all around everything.
Okay, very good. And they're barbed as well, which makes it complex. Kane? Same thing? Any other potential problems? Well, in our research and in my personal experience, those hooks tend to snag things that you don't want them to snag. They'll snag the bottom, they'll snag the grasses, they'll snag logs, they'll snag branches, they'll snag the outside of the fish, and if you're unlucky, they'll snag you. Well, this project was brought to us by a man by the name of Augie Park, who's a professional industrial designer and a weekend warrior who participates in sports fishing competitions. And what he had experienced is the idea of the fish spits the treble hook with frequency. In his own words, he had just gotten done in a competition. He had had a lot of bites, didn't land any of the largemouth bass he was looking for, and he said there's got to be a better way. He came to us with this design. He had filed a patent. He had come up with these beautiful sketches. He had never mocked anything up. He had never prototyped anything, and he brought it to us and said, "Can you do this?" All right, I want you to put your thinking hats on. You're on a design team. You're at a university. Mr. Park has just come to you with this problem. What might you do as your first step?
Go fishing.
Go fishing, sure. Okay, and what would you hope to learn from those similar things? Okay, Claire? Sure, sure. So he's a resident expert. Yep, without question. Okay, so these are great in terms of understanding, is there a market for it? How about, though, if our need is to actually, can we fabricate it? Okay, how would you mock it up? Okay. Okay, so just buying some off-the-shelf hooks and then just seeing if you weld them together, how they might act. Okay.
I would try to ask a fish manufacturer how easy they think it would be to make.
Right, so we did reach out to fish hook manufacturers. Fish hook manufacturers want to have nothing to do with you. They have people knocking on their door every day, come look at my fish hook, come look at my fish hook. Another thing that the students discovered is you might want to research how fish hooks are manufactured. There's nothing in the literature. They're all trade secrets. And so we ended up having to reverse engineer a fish hook. So we took the Eagle Claw trocar, which was the #1 fish hook in the market, and we actually took a very thin cross-sectional slice, and we determined through scanning electron microscopy that we were looking at steel for the hooks and actually brass for the cement, a process called brazing, to hold those hooks together. So there you have, again, this is all in Mr. Park's head. The standard or relaxed in the top left, the engaged on the bottom right. What's happening to those wires, and is there a way that we can model what's happening to those wires? Claire? Right, so the intent here, turns out a largemouth bass is a suction feeder. It sucks it in and then it comes down. The intent is there's a load applied inward, right, on all of those that allows these hooks from being buried to being exposed. If I were to model that, is there anything that you know from your experience in McCormick that could get you started? Well, what if I looked at this as just simply a beam, underload, and bending? EA2, Civil Engineering 216, there is an application for that knowledge. And through this, you can understand the travel, the amount of force that's needed, and maybe what the dimensions need to be. And this led actually to an exploration of lengths and cross sections where we ended up coming up with a sweet spot between the compliance and the stress that this hook needed to experience, which was really good in terms of wire selection and also the length that the wires needed to be. We also looked at fatigue testing, the idea that you wanted to be able to use this hook more than once. You want these barbs to be able to move past each other multiple times. And what I have here is a quick and dirty fatigue testing machine that was created by one of the students on the team, just literally with some scrap acrylic, a DC motor, and inspiration from a locomotive. And he did this literally in an hour. We were at the Museum of Science Fab Lab, and the next thing you know, Izmir's over there with his little device with a wire, and he's got this thing going back about 120 times a minute, and he's just watching how it flexes. The last thing I want to talk about with this project is the idea of if you're using wires and you want to be able to manipulate those wires, and Kane, you had a good workaround using off-the-shelf stuff, the team reached out to a metallurgy professor, and his recommendation was, here's a bundle of piano wire, and you need to heat treat it. So one of the students took this bundle of piano wire, took it home, put it on his gas range, and heat treated it, brought it to class the next day, and it was brittle like pasta. And his words were literally, I think the professor was playing a joke on us. There's no way this is going to work. Well, we didn't give up. We ended up going in and looking at the phase diagram for steel and understanding that heat treating has a great big space. And what we ended up having to do is we had to first normalize the wire. And normalization means you're going to take that wire and you're going to move it up to the austenitic phase, which is, in this case, above 1100 degrees Fahrenheit for over 48 hours. And what that does, it increases the ductility of the wire. So you can do anything you want with it. And that's, in fact, what we did. Then, once it had been heat treated in that way, you can see us forming it, and you can see that we could do whatever we wanted to do shape-wise. But those wires are not strong. You need to go through the process of tempering to do that, which in this case was somewhere around 500 degrees for less time. And that allowed us to create some of these crude mock-ups that you see here. The last thing that we were able to do is use an Instron machine to tensile test, and in a benchmarking sense, the top sellers on the market, and you can see that blue bar, which was our hook, compared favorably in terms of the strength relative to the competition. So what I guess I want you to take home from this is this team knew nothing about metallurgy when they started out. But by the end, they had a great appreciation for, one, phase diagrams, which you often learn in materials science and thermodynamics, but you don't ever do anything with, and that there's a really meaningful application of that science.
Thank you. So yeah, they really went deep, way beyond anything they might have done in their classes, I feel sure. Okay, so it's getting late, and I want to have a few minutes for just open conversation. So I'm going to really abbreviate this. This is the story of image-guided surgery that I promised at the beginning, and I'm just going to kind of show you the beginning and the end. So at that time, again, the objective seemed to be, especially orthopedic surgery seemed like a good target, and why not just make a robot do this stuff right? Never mind that surgeon with their chisel or their drill or their mill. So our concept was keep the surgeon and just use the robot basically to bring imaging information from a CAT scan so that you could execute it, so that the surgeon could execute it, get registered to the anatomy just the right way. And so there's our team. I'll come back to them in a second. The concept had to do with using fluoroscopy, called a C-arm fluoroscope, to take a couple of images of what was originally spine surgery, choose where to insert, in this case, insert a hole for spinal fixation, and we later moved to knees. And I just wanted to highlight a few people. Arthur Quaid did some of the robot calibration. He was a student here in mechanical engineering. Another student did fluoroscope linearization. How do you register these things to each other? And we came up with a system, but what actually went into play in the end was a knee surgery, knee sculpting for a knee replacement surgery system. And there it was a robot-held burr, something that could grind away bone, but with surfaces that were defined in software. So the surgeon was controlling it, the robot was constraining where the cuts went. It's kind of all I want to say about it. So keyhole bone sculpting, that became the Mako Rio system, which was acquired by Stryker. Team members, I'll just point out a few. Hyosig in software, Dennis, software. These people are mostly software, mechanical engineer. So anyway, I was talking to the guy that doesn't have the yacht, and he was just pointing out these extraordinary engineers who were part of the team there. Okay, so that's enough. Let's talk about, well, anything, but design teams, the relationship between design thinking and design engineering and just technical engineering. Thoughts for anybody? Yeah?
Yeah, so if we're talking about the story you just told and then Bishop's story, learning about metallurgy from scratch is impressive, but that's also one thing compared to having to apply your engineering to something like e-surgery
Yeah, that's really interesting. So, so there are going to be compartmentalizations, right? Inevitably. And if you're really, I guess I'm thinking if you're really a valuable compartmentalized wizard, you are also arguably a very valuable design team, brainstorm, that kind of a thinker as well. But in the end, somebody's going to have to go and learn metallurgy, right? And you can leave all of your design thinking behind for a while you go focus on that. And I guess I'm wondering a little why, why are those wizard level engineers anyway so valuable on these brainstorming and design teams? Maybe it's because this is kind of introspection, which is notoriously unreliable. But maybe it's because even though you're trying to be uncritical of your own thoughts and others, really you are. You have a deep sense of what's plausible, what's unlikely. That's a possibility, and that's a good thing, really. And another might be that your breadth of associations, because you've been around a lot and seen a lot of things in your field of specialization, your tentacles out into association land. So those are just a couple thoughts on why I find those engineers anyway so valuable. Yes?
I was just going to earlier you said that one of the main motivations for using this design method is to save time and by really often. And I think if you have people who really know what they're talking about, then they can identify a failure before you can always make that outcome. They might get
Yeah, although I think in my experience, the ones who sort of said that's a failure, even if they were the ones who invented it, were more the domain experts and the people we went outside for. I guess there were things that we went like, oh, this is just technically never going to work. Are you sure it's never going to work? Yeah, I'm sure it's never going to work. So that's where the technical wizard, you might say, yeah, you're probably right then.
Michael, I want to comment on Daniel's question a little bit. I haven't taught this class the last couple of years, but historically I've taught the BME capstone and I've taught the mechanical engineering capstone. And what Professor Beltran and I have found is that mechanical engineering seniors can do a pretty good job on biomedical problems. There are biomedical problems that there's a paper out there that talks about the emergent properties of biological systems, and there are emergent properties. But a lot of biomedical problems can be distilled to electrical, mechanical type problems, and you learn the physiology you need to learn to complement that. I'm not saying it's universal, but in our experience, we found that our students can come up to speed on the biology as needed. Any other questions?
Thoughts? Speculations?
Lauren?
For what?
Well, in that case, and I can't give you a direct answer, right? It depends on the project. In this project in particular, they were working with a company called Chandler. They met with that company 4 separate times, and pretty much what happened is, here's our proposed solution. They said, that's not going to work, that's not going to work, that's not going to work. The team came back to campus, brainstormed, well, what can we do? And what they found is that the simulations, because the geometry was simple enough, that they were able to do those things in silico. If you were actually going to try to do that through 3D printing, it would be just way too time consuming and you wouldn't be able to iterate. So in this case, I guess the simulations were accurate enough for the system that they were designing that they were able to do it in a very efficient way.
There was a question earlier about some expert is going to be able to tell you early on, yes or no, this is going to work. How would you say that students can reach that point?
I don't think it can be taught. I think it can be learned. And I think one of the things that we do within McCormick is we give students the opportunity to take ownership of that knowledge. There is something about working on projects where you care about that project, that the knowledge that you gain, that you apply, that you transfer, you own. And if it's just going into an exam, it's going into a quiz, you don't tend to own it and retain it and keep it with you in the same way. I'm not saying that that's a universal answer, but I think it's at least one way.
Well, it really is 5:15. I suppose we should let you go. Thank you for attending today.
Yes, thank you. It was great to have an audience.